Hey guys, and welcome to 8.3. So this time we're not going to start off with the video because we're going to get to the video a little bit into this lesson. So 8.3 is about the Pythagorean Theorem. The famous a squared plus b squared equals c squared. You probably thought when we were doing geometry that this was going to be one of the main things that we do. This, and then like area and perimeter. Well, we are going to start talking about area and perimeter a little bit today, but area and perimeter don't really happen until Unit 10. All right, so 8.3 is all about Pythagorean Theorem, and we're going to use the Pythagorean Theorem and its converse to solve problems. We're also going to get a little bit into Pythagorean triplets. So let's get started. So first, the Pythagorean Theorem is a squared plus b squared equals c squared. So a and b don't really matter which leg it is, but a is the length of one leg, and b is the length of another leg. The two legs of a right triangle make the right angle. Because c, the hypotenuse, now c is always the hypotenuse. And you can tell which side is the hypotenuse. One, because it's always the longest side, and two, because it's always across from the right angle. So it's going to be a squared plus b squared equals c squared. The length of one leg squared plus the length of another leg squared equals the length of the hypotenuse squared. So let's take a look at one proof of the Pythagorean theorem. So we have A, B, and C. So A is going to be our long leg, B is going to be our short leg, and C is going to be the hypotenuse. So let's say that we create a square where we take this triangle and kind of rotate it 4 times over. So now we have a big triangle, a little triangle, and 4 congruent triangles, 4 congruent right triangles. So let's first find the area of the outer square. So areas of squares would be like height times width or length times width, however you want to think about it. So this length is a plus b, and this width is also a plus b. So the area of the outer square is a plus b squared. The area of the inner square, this length is c times this length is c, so that would be c squared. And the area of each triangle, so remember the area of a triangle is 1/2 base times height. So it's going to be 1/2 a times b or b times a. Doesn't really matter. So 1/2 a times b. So what we know is that the area of the whole square, a plus b quantity squared, is equal to 4 of the triangles plus the little triangle, the inner square. So we have a plus b squared equals 4 times 1/2 a plus b plus c squared. The outer triangle equals the outer square equals the 4 triangles plus the inner square. So let's expand a plus b squared, and we get a squared plus 2ab plus b squared. And let's distribute this 4. So 4 times 1/2 is 2, and then so this is going to be 2ab plus c squared. Then we have a 2ab over here and a 2ab over here, so we can subtract 2a on both sides. Oops, sorry. 2ab on both sides. And then what we're left with is a squared plus b squared equals c squared. So this was one way to prove it. Now I want to show you another way without doing algebra. And I'm not going to show you. It's going to be from this amazing person who's done really, really cool YouTube videos called Vi Hart.
You don't need numbers or fancy equations to prove the Pythagorean theorem. All you need is a piece of paper. There's a ton of ways to prove it, and people are inventing new ones all the time, but I'm going to show you my favorite, except instead of looking at diagrams, we're going to fold it. First, you need a square, which you can probably obtain from a rectangle if you ask nicely. Step 1, fold your square in half one way, then the other way, then across the diagonal. No need to make these creases sharp. We're just taking advantage of the symmetries of the square for the next step, but be precise. Step 2, make a crease along this triangle parallel to the side of the triangle that has the edges of the paper. You can make it anywhere you want. This is where you're choosing how long and pointy or short and fat your right triangle is going to be, because this is a general proof. Now when you unwrap it, you'll have a square centered in your square. Extend those creases and make them sharp, and now we've got 4 lines all the same distance from the edges, which will allow us to make a bunch of right triangles that are all exactly the same. Step 3, fold from this point to this one, basically taking a diagonal of this rectangle. Now we've got our first right triangle, which has the same shape and area as this one. Let's call the sides little leg, big leg, and hypotenuse. Rotate 90 degrees and fold back another triangle, which of course is just like the first. Repeat on the following 2 sides. The original paper, minus those 4 triangles, gives us a lovely square. How much paper is this? Well, the length of a side is the hypotenuse of one of these triangles, so the area is the hypotenuse squared. Step 4, unfold, and this time let's choose a different 4 triangles to fold back. Rip along one little leg and fold back these 2 triangles. Then you can fold back another 2 over here. The area of the unfolded paper minus 4 triangles must be the same, no matter which 4 triangles you remove. So let's see what we've got. We can divide this into 2 squares. This one has sides the length of the little leg of the triangle, and this one has sides as long as the big leg. So the area of both together is little leg squared plus big leg squared, which has to be equal to this area, which is hypotenuse squared. If you called the sides of your triangle something more abstract, like a, b, and c, you'd of course have a squared plus b squared equals c squared. So quick review. Step 0, acquire a paper square. Okay, step 1, fold it in half 3 times. Step 2, fold parallel to the edges anywhere you choose and extend the crease. Step 3, fold back 4 right triangles around the square and admire the area hypotenuse squared that is left over. Step 4, unfold and rip along a short side to fold back another 4 right triangles and admire the area, one leg squared plus the other leg squared that is left. And that's all there is to it. Of course, mathematicians are rebels and never believe anything anyone tells them unless they can prove it for themselves. So be sure to not believe me when I tell you things like, this is a square. Think of a few ways you could convince yourself that no matter what the triangles on the outside look like, this will always be a square and not some sort of a rhombus or parallelogram or dolphin or something. Or, maybe it is a dolphin, in which case you should define what a dolphin is and then show that this fits that definition. Also, these edges look like they line up together. Do they always do that? Is it exact?
Now that we have seen different proofs of the Pythagorean theorem, let's start applying the Pythagorean theorem. So find the value of x, and your answer should be in simplest radical form. So for this whole unit, everything should be in simplest radical form. Simplest radical form. We won't be doing anything into decimals. Even if it says put it into decimal around to the nearest tenth, that probably means that I forgot to change the instructions to simplest radical form, because everything, all your answers should be in simplest radical form. Okay, so we have short leg is 2, long leg is 6, and the hypotenuse is x because it's across from the right angle. At this moment, we wouldn't know that it's the longest side length, but since it's across from the right angle, it must be. So we can set up the equation of 2 squared plus 6 squared equals x squared. So 2 squared is 4, 6 squared is 36, and x squared is x squared. So 4 plus 36 equals 40. We will then do the square root property. There we go. We'll do the square root property of equality and take the square root to both sides. And we get that x is equal to the square root of 40. But remember, we can simplify the square root of 40. So let's bust out our perfect squares, which are 4, 9, 16. I don't have to go any further because the next one, 25, is greater than half of 40. So obviously none of those are going to go into it. So let's see, does 16 go into 40? Nope, because 16 times 5 is 50, and then so 16 times 4 obviously won't go into it. How about 9? Nope, because 4 plus 0 does not equal 9, but yep, 4 does go into it, and it's 4 times 10. So we can write this as the square root of 4 times 10, or equal to 2 radical 10, or 2 square root 10, 2 root 10. So that is 2 root 10. And you might be saying, like, 2 root 10 is greater than 6? Well, yeah, because root 10 is somewhere between 3 and 4, and 2 times somewhere between 3 and 4 is going to be greater than 6. Because 2 times 3 is 6. Anything that's 2 times a little bit higher than 3 is going to be greater than 6. All right, example 1b. Find the value of x and give the answer in simplest radical form. All right, so this time we have 2 x's. So it's going to be a squared plus b squared equals c squared. So x minus 2 squared plus 4 squared equals x squared, because x in this case is the hypotenuse. All right, so we're going to have to expand this x minus 2 to get x squared minus 4x plus 2. Remember, we can't just do x squared minus 4, because this is x minus 2 times x minus 2. So we'll have to FOIL. And then 4 squared is 16. Let's combine like terms and bring this x squared over to the other side. And we get that negative 4x plus 20 equals 0, because the x squares cancel each other out. Then we can solve this like any other linear equation. So we're going to subtract 20 on both sides. Or I guess we're going to add 4x to both sides. And then divide by 4 to get that 5 equals x. So we didn't even have to put it into simplest radical form, because 5 is already in simplest radical form. The radical is invisible. All right, so that is solving using the Pythagorean theorem, but there's also something called Pythagorean triplets. And a Pythagorean triplet is a set of 3 non-zero whole numbers, so a, b, and c, such that a squared plus b squared equals c squared. So the common Pythagorean triplets are 3, 4, 5, 5, 12, 13, 8, 15, 17, 7, 24, and 25. Whoops. I highly recommend memorizing these 4 Pythagorean triplets. It makes it so much easier for a lot of problems, because how like tests are made, and even with standardized tests, they tend to like to have nice numbers, and these are the nice numbers that they would have with these types of problems. So it's a good idea to memorize these 4 triplets. Also, any multiple of the Pythagorean triplets also work. So like if you multiply all of these by 2, so like 6, 8, 10 would also be a Pythagorean triplet. Or if you multiplied all of these numbers by 7, that would be a Pythagorean triplet. But you just have to make sure, like if you multiply by like 7.5, if any of the numbers end up not being a whole number, then that's not a Pythagorean triplet anymore. And like 7 times 7.5 is not a whole number, so we can't like multiply it by that. So let's look at this. Find the missing side length and tell if the side lengths form a Pythagorean triplet. All right, so we have a squared plus b squared equals c squared. So 14 squared plus 48 squared equals c squared, the hypotenuse. So we get 2,500 or 2,500 equals c squared. We take the square root and we get 50. All right, so we have 3 integers, 14, 48, 50. So that must mean that this is a Pythagorean triplet. But which of the basic triplets is it? Well, if we divide 14, 48, and 50 by 2, we get 7, 24, and 25. And so this is the 7, 24, 25 triplet, or 14, 48, 50 triplet. And then for our last problem, find the missing side lengths and tell if they are Pythagorean triplet. So we have 4 as one leg and 12 as the hypotenuse, because it's across from the right angle. So that means C is going to be 12 and A is going to be 4. But it's totally fine if B was 4. Just one, either A or B would be 4. So we get 16 plus B squared equals 144. And then we subtract 16 on both sides, and we get that B squared is equal to 128. Now, 128 is not a perfect square, so we already know that it's not going to come up to a whole number, a positive whole number, a non-zero whole number. So we know that we're not going to get a Pythagorean triplet, but we can still solve for B. So we can take the square root of 128, which ends up being 8 radical 2, because 64 goes into 128 2 times. All right? The side lengths do not form a Pythagorean triplet because 8 radical 2 is not a real number. It's not a whole number. So there should have been some space, but that says whole. All right, that is it. Thank you guys for paying attention and following along. Please attempt the online quiz at least 2 times if you don't pass it the first time, and I will see you guys soon.